Welcome to the Chemistry, Biology and Math Revision Hub. Today we'll be doing the January 2022 Section B and C, Unit 4 Chemistry for Pearson Edexcel International A level. So I will go straight to the first question of Section B. They say, bromate 5 ions oxidize bromide ions, Br minus in dilute acid. So this is the equation for that reaction. They say experiments to determine initial reaction rates were carried out using different initial concentrations of the three reactants. And the results are shown in the table here. So those are the results. The first question says, the reaction is first order with respect to bromate, 5 ions. Deduce the rate equation for the reaction and justify your answer using the data. So this is what we have. It's first order with respect to bromate. So it means we know the order with respect to that. We need to find the order with respect to H plus and the order with respect to Br minus. To find the order with respect to H plus, we need to keep the other two reactants constant as we vary H plus and then be able to predict the order of that basically for H plus. So what I did here, I first found the order with respect to H plus. So when we see experiment 1 and 2, the bromide ion concentration is constant, and here the bromide concentration is constant, while this is multiplied by 2. So if I feed into my rate, my new rate is going to equal to K into the concentration of bromate, which are going to be exactly as they were originally. Concentration of bromide is going to be still the same. And then concentration of H plus, which is actually 2 times. So it's going to be twice the original concentration. Now, I know this is first order. However, I do not know these orders, and let me call them A and B. So when I do this, they say, when you look here, when I vary the concentration of H plus, the order increases with a factor of 4. So what am I going to get out of here to make this rate be 4 times the original rate? Since this remained unchanged and that is unchanged, it means the only difference is going to be created by the 2 in here. And how does a 2 become 4? A 2 becomes a 4 only if it's going to be squared. So here we can see, because B is equal to 2, the order with respect to H plus is going to be second order. So we have been able to establish this. So it's going to be second order with respect to H plus. Then I will go to the next part, trying to find the order with respect to Br minus. So again, the equation will be similar to that, but in this case, we have rate is equal to K. Now, I want to find out which experiments I'm going to use to predict the second one. Let me use experiment 1 and 3. In 1 and 3, here we can see that the concentration is multiplied by 1.5. And here, of course, we can see that is multiplied by 2. And this is kept constant. The rate increases by a factor of 3. So I'm going to feed them in this equation and try to calculate. So the bromate is multiplied by 1.5, so it's going to be 1.5, the original Br03 minus. We know it's first order. The bromide concentration is multiplied by 2, so twice Br minus. Bromide, we do not know, so let me call it order A. And the acid is kept constant, so it's going to be exactly the same, H plus. We know it's second order. So I want to make sure if the original reaction was red, is equal to K before the change, concentration of bromate minus concentration of bromide power A and concentration of acid power 2. Because this concentration here, again, they've told us when I do that, this is going to be 3 times. This should be 3 times the original one. And to do that, it means I will do this. I will multiply that and the 2 here. A 1.5 times 2 gives us a 3. So it means because this came out as a 2 and not a 4, that is also going to be 1. So it means it's going to be first order with respect to bromide, as you can see here, first order with respect to bromide. So because it's first order with respect to bromide, first order with respect to bromate, and second order with respect to H plus, my final rate equation is going to be as you see here. So we're going to continue on to the next part. Using the data from experiment 4 and your answer in, of course, A1 to calculate the rate constant for the reaction, include units in your answer. So here, let me again first remove that to make it neater. So they say rate, this is what we had as the rate equation from the previous page. So here what we have to do is make the K the subject and substituting the value from the table, basically, experiment 4 in the table. I want to take you back slowly. Experiment 4, these are the results we're going to use in. Again, when I do that, let me take away that to make it neater so that you can see everything clearly. So this is what we're going to use. This is going to be what we feed in as the red, and these are the individual concentrations we're going to feed into our calculation on the next page. So let me go back slowly. Yeah, this is what we fed in here, and then here the final answer was 0.014889. You have to take care of the units. It's decimeter per 9 mole cubed per second. So I will go to the last question here. Part B says, give one possible reason why the rate equation shows the reaction cannot proceed in one step. If we go back, again, sorry, let me take you back here. Here, when we go back, actually, we have this reactant, and that reactant. So I want to take you down here. So here we have many reactant particles. Actually, again, to take you back, when you count them, they're going to be 1 bromide, 5 bromide, and 6H+. If you consider this is going to be a total of 12 reactant particles. 12 reactant particles are being combined, and when you combine them, it is going to be harder for 12 different particles to all collide in one step and be able to give you a product. So maybe two reactants can collide in one step, but 12 different reactant species colliding, 12 reactant species or particles colliding successfully within one step is going to be really hard. So any reaction involving more than 2 particles is unlikely to occur in one step. So that is why this is not possible to occur in one step. Question 19. Propanol reacts very slowly with HCN at 298 Kelvin. To increase the rate of reaction, potassium cyanide is added. Actually, the reason for this is HCN is kind of not good at dissociating to release the H+ and the Cn-. So it means we're going to have fewer Cn- ions interacting. So we add in the KCN. The KCN is good at dissociating. It will produce a lot of Cn- freely available, and these will attack, and the reaction will proceed really fast. And this is going to be a catalyst because it's going to be regenerated at the end of the reaction. So they say complete the mechanism for this reaction by adding curly arrows and relevant lone pairs and dipoles to step 1 and 2. So I'm just going to remove this, put it there. Let's see how you do this mechanism. So we begin off by putting the lone pair here, and then you position the sigma plus and the sigma minus here, because there is a difference in electronegativity there, and therefore there is going to be a partially positive carbon. Now the partially positive carbon is going to receive a lone pair from the other carbon, and when that occurs, this bond is going to break, returning the lone pairs to oxygen, forming this intermediate here. And then in the next step, we can see here, of course, this one here, there is a lone pair that was returned. This lone pair is going to be donated to here, and that bond will break, returning the electrons to the other side, forming the product. So here, if we have to do, actually we are not required to draw the products, it's just these 2 steps, and as you can see, that is what is going to occur in this reaction. So the next part says, explain why the reaction between propanol and HCN in the absence of KCN is very slow, referring to the value of Ka. No calculations are required. And again, as you can see, because HCN is not good at releasing the H+. So basically, the constant Ka, the equilibrium constant Ka, is not going to be really high. It's really small because, of course, there are going to be fewer products produced, and most of it is going to be a reactant. So there is weaker dissociation here. So I say the value of Ka for HCN is very small. As you can see, it's really small. So this will show that equilibrium will be reached when small amount of Cn- is going to be produced. Equilibrium here is going to be way towards the left, meaning fewer amounts of Cn- will be available, and the reaction cannot proceed really fast. So the low concentration of Cn and minus ions will limit the rate of this reaction. So to enhance this reaction, we will need to put KCN, which is good at contributing towards the concentration of Cn-. The next question says KCN is a homogeneous catalyst in this reaction. Justify this description by referring to the mechanism. Guys, here we have to know what homogeneous means and what a catalyst means. So Homogeneous because it's in the same phase as the reactants or as the components basically. And again, it's a catalyst because it causes the reaction to speed up, or it raises the reaction to completion. So I said it increases the rate of reaction by providing CN ions required. Also, the CN ions are going to be regenerated in step 2, so this explains it's a catalyst. And then the next part, it is in the same phase as the reactant. So here this part is explaining the homogeneity or homogeneous part. It's in the same phase as the reactants. And then the part generating, explaining why it's a catalyst is because it provides Cn minus ions in step 1. However, in step 2, it is regenerated, so it was a catalyst in this reaction. The next question says the organic product of this reaction are enantiomers. Draw a 3-dimensional structure of these enantiomers. So the enantiomers produced, of course, it's going to be CH3, CH2, a C or H here, a hydrogen here, and a CN here. So we have to draw as enantiomers, meaning we have to use the wedges as well as the dotted arrows. So in this case, this is in my dimension, and this one I can see it, but the other is towards the other side, and this is moving away from me towards the other side. So you have to learn how to draw these 3D wedges because they are required if they ask you to draw a 3-dimensional structure. So if you put a mirror like this, you will see that that and that are like mirror images, because this part here is similar to that. This part is similar to that. It's like mirror images of each other, and this is far away as well as that. If you can observe, I even drew the atoms as if it was exactly a mirror image. You can see how I drew that and that to be facing in that direction. So let's continue to the next part. Question 20. This question is about compounds with a molecular formula: carbon 6, hydrogen 12, or 2. They say hexanoic acid, carbon 5, hydrogen 11, COH is a weak acid. They say write an equation for the dissociation constant Ka of hexanoic acid. So it is written like this. Of course, dissociation is when you split this part apart, so producing a carboxylate as well as the H+. And since they want us to find Ka is always concentration of the product. So we have this product and we have that product. So we put them in concentration brackets and then multiply them, divided by the concentration of reactants. This is how you find the Ka value. The next part says, calculate the pH of a 0.1 mole per decimeter cubed solution of hexanoic acid, provided the Ka is given like that. Again, I refer back to my equation, which I have up there. And then in this here, I say, because we were given pKa, and you know pKa is equal to negative log Ka. Negative log Ka is going to be 4.88, meaning the real Ka is going to be 10 power negative 4.88. To convert this to that, you just say 10 power negative 4.88. And when you use your calculator, you get this value. So this is the Ka value. I can be free to substitute this in this part here. And then also, I need to make sure that you show the examiner. You need to make sure you show the examiner that because, let me go back, because the acid as well as this are coming from here, it means their concentrations are going to be identical because they're coming from the same thing. So I say, since this concentration here is identical, and the assumption I made is we will say the initial concentration of the acid and the concentration of the acid at equilibrium is almost equal because there was very low dissociation. I'm going to take you back again to the equation. In this equation, because this dissociates in a really low level, we assume that the concentration of this initially is going to be equal to the concentration of this after the dissociation of these two has occurred, or after these two have been produced. And even after the production of this, the amount of that, concentration of that and the concentration of that are going to be exactly the same. So knowing those conditions, I can substitute, since this is equal to that, I can substitute them into my original equation, substituting for H plus instead of the carboxylate. So it's going to be H plus times H plus, which gives you H plus squared, divided by the concentration initial, since we have established that the initial and that at equilibrium is exactly the same. So you can remember from the question that they say the original concentration, basically, original concentration is going to be this. So we can substitute that here and make H plus the subject, and this comes out as this. Now, since we know pH is negative log of hydrogen ions, and we know the hydrogen ions, I just feed this here, and I get pH equal to 2.94. So let's continue to the next part. The next part says the solubility of hexanoic acid in water is 1.08 gram per 100 grams of water. The isomer of hexanoic acid, butyl ethanoate, has the solubility of 0.68 gram per 100 grams of water. So here we can see this is less soluble, the other is more soluble, because here less can dissolve, and here we can see we can dissolve more in the same volume of water, same mass of water. So they explain the difference in the, let me remove this to read the question properly. Explain the difference in these data in terms of hydrogen bonding between hexanoic acid and water, and between butyl ethanoate and water. So here we can see that both butyl ethanoate and hexanoic acid, of course, have this carbonyl group, and that carbonyl group is actually polar. Because it's polar, it can be able to form intermolecular hydrogen bonds, or it has a lone pair that can be used in the formation of intermolecular hydrogen bonds with water molecules. Hexanoic acid also, you can see, has OH groups. Because of this OH group, it can form more intermolecular hydrogen bonds with butyl ethanoate, and this is going to be the reason as to why there is this solubility, why one is more soluble than the other. The hexanoic acid has this group. Let me take you back. It has the carboxylic group, which has the carbonyl looking part and the OH part, while the other one, which is a butyl ethanoate, just has that. So there is solubility for that. There is solubility because of the lone pair, but it's going to be really, really weak. But this one here can have that and that, which enables it to be actually more soluble in water. I hope you understand this answer. Part B, compound A is thought to be another isomer of hexanoic acid. 10 grams of compound A is found to contain 6.21 grams of carbon and 1.03 grams of hydrogen, with the remainder being oxygen. Use the data to calculate the empirical formula of compound A. You must show all your working. So in this case, since we have to find carbon, hydrogen, and oxygen, and again they told us this contains only carbon, hydrogen, oxygen, they've given us the mass. We need to be able to find the mass of oxygen. Since the compound was 10 grams, subtract the mass of carbon and the mass of hydrogen, we can be able to get the mass of oxygen. So when we try to find our empirical formula, we'll have all the masses. So this is the mass of carbon, mass of hydrogen, and mass of oxygen. I divide the masses by the atomic mass of each, and then I'll get the number of moles. And then I divide through to get the smallest whole number ratio, dividing through by the smallest number of moles. I end up with this. So this is the empirical formula of course, compound A. The next step says, state how you might use your answer and, of course, the mass spectrum of compound A to prove that compound A is an isomer of hexanoic acid. So here, of course, you have to look at the mass spectrum, look at the molecular ion peak, and then use the molecular ion peak. And in this case, of course, it is 116. We will get the molecular ion peak and then use this. So, of course, you can say C3H6O times N is equal to 116 and find out the possible value of N. Then you can multiply that N with the other carbon and hydrogen and oxygen to be able to find the molecular formula. However, in this case, if we want to prove that A is an isomer of hexanoic acid, we will use the molecular ion peak of compound A. And if it's 116, then we have the same molecular mass, and therefore it's going to be an isomer. That is going to be perfect. So this is this part here is how you would answer this. If you're not given any more information, look for the molecular ion peak, and if it's 116, then it means it's going to be an isomer. And again, if they say, because the hexanoic acid has a molecular mass of 116, so if the compound A and hexanoic acid have the same molecular mass, or if they have the same molecular ion peak, then it means they are basically isomers, because isomers have the same molecular mass. The next part says a series of tests was performed on compound A. Okay, let's see. They say addition of phosphorus pentachloride. Phosphorus pentachloride is to test for presence of OH. It could be OH alcohol or OH carboxylic acid. So here they say misty fumes. If misty fumes are present, it means there is an OH group present. It could be an alcohol or carboxylic acid. And then they say they added 2,4-dinitrophenyl-hydrazine and an orange precipitate was observed. That shows you if there is an orange precipitate, so there is a carbonyl group. Then they say addition of Benedict or Felling solution remains blue. So here we see if it remains blue, it means although we have proved that it's a carbonyl, It is not an aldehyde, so it should be a ketone, because a ketone is the only carbonyl that cannot give a positive test with Benedict and failing solution. So part 4 says additional potassium dichromate. The solution remains orange, meaning this whatever was in here was not oxidizable. Here, so it rules out the idea that this OH was for alcohol. So here we can confirm that the OH actually was either carboxylic acid or it was a tertiary alcohol, but not primary and not secondary. The next part says test using a polarimetry and a plano polarized light is rotated. That means there is a Kairos center in here. So they're going to say deduce the structure of A. This is the molecular mass we know, molecular formula, and justify your answer using all the tests. So the first part, using A, so here we can see from the first part, of course, we're going to use the molecular mass of the molecular formula, this. And then the misty film suggests presence of OH group, which could be alcohol or carboxylic acid. The orange precipitate, or giving a positive test, suggested there was a carbonyl, which could be aldehyde or ketone. And then the negative test with Benedict of failing solution proves that it's not an aldehyde. Therefore, we can confirm because it's a carbonyl, it should be a ketone. And then the negative test with acidified potassium dichromate suggests that A is not a primary or secondary alcohol and A is not an aldehyde. And finally, rotational plane polarized light in a polarimeter suggests a Kairos center. So we begin off by showing our Kairos center. Remember, there is OH group. And then we know that actually this is a ketone, so we can position the ketone. Again, remember there are 6 carbons, so if there is a Kairos center, there is a possibility that these are going to be carbons, and if one is a CH3, one could be a CH2, CH3. They cannot be exactly the same, leaving only with a CH3 this side. So it can be easy to predict which compound will have the same molecular mass. So basically, again, remember, it is going to be a form of, this is going to be a ketone, which is an alcohol, and it has a Kairos center. So it means that is the only possible structure we can get. So I will move on to the next part. Lastly, it says compound B, another isomer with a molecular formula carbon 6 hydrogen 12 O2, contains a ring of 6 carbons. So they say the carbon 13 NMR spectrum has only 2 peaks, one at which is basically at 69 ppm. So they say draw the structure of B. Possibly because, of course, they've told you it has a ring, a 6 ring. So you begin by drawing the 6th ring. And then another thing they've told you, it has only 2 peaks in the carbon 13 NMR, meaning these carbons, of course, the carbon peaks are going to be that are identical, that and that are identical. It means there is no other carbon outside, meaning since all the carbons are within the ring, it's only for 2 oxygens and 2 hydrogens that are left, so it should be a diol. And therefore, this brings us to the end of this part. Let's continue to question 21. Question 21. Esters are used in flavorings and perfume. They can be made by reactions involving alcohol. A flask containing a mixture of 0.2 mole of ethanoic acid and 0.150 mole of ethanol, so of course this is esterification, was left at 25 degrees in the presence of a catalyst until equilibrium had been established. I usually like presenting my results like this. If there is an equation given, I write the data below the equation so that I have all the information before I do my calculation. So they say in the presence of a catalyst until equilibrium had been established. Then they're going to say the ethanoic acid present in the equilibrium mixture required 34.8 centimeters cubed of 2.5 mole per decimeter cubed solution of sodium hydroxide for complete neutralization. Calculate the value of the equilibrium constant Kc for this reaction. So here we see we have when you write the equation between, of course, ethanoic acid and sodium hydroxide, we will produce sodium ethanoate and water. This is what is going to occur when you have the reaction between sodium hydroxide and ethanoic acid. We were given the information here. They said 2.5 mole per decimeter cube. Again, you see ethanoic acid, equilibrium, with the mixture required that of that sodium hydroxide. So we have the information for sodium hydroxide, and we have the information for, of course, for everything. So and again, ethanoic acid present, the mixture required that of that solution of sodium hydroxide. So we will begin by finding the number of moles. So I said here moles of ethanoic acid left, because those that were left are the ones that are going to be equal to the number of moles of sodium hydroxide that reacted. So this is going to be concentration times volume. So we know we have the concentration 2.5 times 34.8 over 1,000 gives that. I'm going to position this somewhere here. So here we can see when we have those number of moles, it means these are number of moles that actually reacted, sodium hydroxide that reacted. And then we can come back to our original reaction. As you can see this reaction here, I rewrote it here with the information we had. This is the reaction here. And here I'm going to work with the initial moles. Initial moles was 0.2 for ethanoic acid, and there was 0.15 for the alcohol as given. So the 0.2, 0.15. So we need to find the initial moles, find the change that occurred, and then the moles at equilibrium. So the moles of the product initially were all 0 because there was no product formed. However, let's look at the change. The change that occurred is that 0.113 moles were actually formed. The reason for that is we can see this was left at equilibrium. If this was left at equilibrium, yet, let me use red here so that we can see. This was present initially, but this was left at equilibrium. Because this was left at equilibrium, we get the difference between these two, and it means 0.113 was the change. So we can see the change was 0.113, and therefore it means the moles of the product were each 0.113. That is the change that occurred in the product. So there was a positive plus change, and this is the total moles at equilibrium for the product. Now, remember again, the reaction ratio is basically going to be, for this one here, it's going to be 1 to 1. 1 mole of ethanoic acid reacts with 1 mole of ethanol. And also, because they reacted in a ratio of 1 to 1, the change that occurred here should be a loss of 0.113 moles. So when we subtract 0.15 minus 0.113, we get 0.037. So when we conclude here, we can see that the moles of ethanoic acid present were this at equilibrium, the moles of the ethanol left were that at equilibrium, and the moles of the products were equal because actually the reaction ratio was a 1 to 1, producing a 1 to 1. And again, if I take you back up here, remember, I want to reread that part. They said a flask containing 0.2 mole of ethanoic acid and that of ethanol was left in the presence of a catalyst, meaning a reaction occurred between them. And then they say the ethanoic acid present in equilibrium mixture required that. So it means the ethanoic acid left, that is the unreacted ethanoic acid, required 34.8 centimeters cubed of 2.5 solution of sodium hydroxide. So this is the information of sodium hydroxide. To find the number of moles of sodium hydroxide that reacted with the ethanoic acid, those are the moles because it reacted with the ethanoic acid that was left, the unreacted, the one that was left over in the first reaction. So these are the moles that was 0.087. That means at equilibrium, there was 0.087, and then we used that to be able to get the difference, which was 0.113, and that would be that for the product. And the difference here would be also 0.113, giving us that. After finding all this concentration, we can put it into our Kc equation, and therefore Kc, referring back to this part, this is the equation we're interested in. We're going to use that to find Kc. It should be the concentration of all the products divided by the concentrations of the reactants. So here we see the concentration of the ester times the concentration of water divided by the concentration of the ethanoic acid and the concentration of ethanol. So when we substitute, remember all these are in equal volume. So even if we do not have the real concentration, we just have number of moles. Keeping in mind that they are in the same volume, it means the volume function. Actually, volume cancels out. So that's why here you see I put moles over volume to give you concentration, moles over volume to give you concentration, still moles over volume to give you concentration, and moles over volume to give you concentration. But since the V up and the V below are the same, they cancel out, and I get those moles. So since I'm getting moles, you can see 3.99. If you round off, you can say 4. This is going to be Kc, and it has no units because all the units are going to cancel out. So the next part says the enthalpy change for this reaction is small, explained by reference to the type and number of bonds being broken and made how this might be possible. Now, enthalpy change using bonds broken and bonds formed is given by this equation. Enthalpy change is equal to the summation of bonds broken minus the summation of bonds formed. If you go and look back, it's almost the bonds broken and the bonds formed are almost the same. And again, let me take you back slowly. Ethanoic acid, let's see. Ethanoic acid has carbon, oxygen, and oxygen, hydrogen. Ethanol has oxygen, hydrogen. I'm looking at a stronger bond basically. If you're breaking, then the ester has oxygen, of course, oxygen, carbon, a single bond, and carbon, oxygen, double. Also, the ethanoic acid has the carbon, oxygen as well. Then in the product, of course, it's similar as if we have the same types of bonds being broken. A carbon-oxygen double bond, an oxygen-hydrogen, and the carbon-oxygen single bond in the reactant side as well as the product side. It would be safe to say that the net bonds broken are almost identical in the reactants. They are identical to those formed in the product. So here I said, if the enthalpy change is small, then it's because the types of bonds broken and those formed are almost the same. So you can see carbon oxygen and oxygen hydrogen, and the number of bonds in each type broken is the same as those being made. So therefore, the enthalpy change is almost the same. It's small. An ester which smells of raspberries can be formed by either two different reactions. So we have two reactions here we're going to use. There is reaction 1, whether we have a carboxylic acid combining with an alcohol to form an ester and water. This is esterification. This is what we call esterification. Or here we can use, of course, a chloride basically and an alcohol to form that. This reaction here is reversible, so of course the yield is not going to be that great. However, this one is going to have a higher yield, but it will have HCl, which is a toxic gas, so that one you should know. So they say, name the carboxylic acid, alcohol, and catalyst used in reaction 1. Reaction 1, the carboxylic acid is methanoic acid. Of course, this one here is methanoic acid. The catalyst used is concentrated sulfuric acid. And then the product is 2-methyl propan 1O, because you can see when you count the bonds, it's easy to name that. And then they say explain one advantage and one disadvantage of using reaction 2 rather than reaction 1. The advantage is reaction 2 has a higher yield. The reason, remember again, they're asking you to explain one advantage. So you state the advantage and explain it. It has a higher yield because it's not an equilibrium reaction. The reaction goes to completion, so there is going to be a higher yield of the ester. Also, it does not require a catalyst, so it's not the costs. Remember, when you use a catalyst, you have to separate it from the product. So because reaction 2 does not use a catalyst, the costs of separation of the reactant, the catalyst from the product, are going to be minimized. And the reaction 2 does not involve heating, meaning energy requirements are not required, are going to be basically lower. So the disadvantages are, of course, HCl gas is produced. This can be corrosive because it's an acid, and it's also, so basically the plant setup has to be corrosion resistant. It has to have equipment that can deal with acidic conditions, and those equipments, of course, are going to be very expensive. And another thing, HCl gas is toxic. And so also you need to use a fume cupboard when you're using this. So those are the advantages and the disadvantages. This brings us to the end of section B of this paper. Let us continue on to section C. Section C, question 22. The equation for the formation of ammonia in the Haber process is as shown below. This is the equation. They say at 298 Kelvin, the standard entropy change of the reaction, the S system, is equal to negative 98 joules per Kelvin per mole. And they say, calculate the standard entropy of 1 mole of ammonia. So they say use the value of the S theta for the system and the data in the table. So we're using the values in the table, and they want us to find, of course, the missing value. So this one here, they want us to calculate the standard entropy of 1 mole of ammonia. So here, I said if you want to find the S system, it's going to be the entropy of products minus the entropy of reactants. So since we know the S system from here, and we know the entropy for basically the reactants here, they've given them to us, we can be able to predict that for ammonia. One thing we know is we're using half of nitrogen and 1.5 of hydrogen. So this is per mole, so we have to multiply by the number of moles. This is going to be a half times 192. And that is going to be 1.5 is 3/2. So 1.5 is the same as 3/2. So 3/2 times 130. one which is for hydrogen. And then when we add up everything and make this the subject, we end up with this. Now, the key thing to remember is you have to be able to put, again, I'm going to put, this is going to be, so it came out as positive, so I'll just write positive, but it's going to be joule per Kelvin per mole. I will go to the next part. They say the value of the total entropy, the S, of course, total varies with the temperature. Data for the values of the S total at different temperatures, but at standard pressure of 100 kilopascal are given for this reaction. So we can see all these values, and they want us to plot basically on the next page. So looking at these values, I'll move on to the next page. Sorry. So the next page says, let me make it smaller so that you can see, plot a graph of the S total against 1 over T on the grid. So here you have the scale is already, everything is already done for you. So all you need to do is find the correct points where you can position your data and then draw the line of best fit in order to be able to, because they asked you to include a line of best fit, so you have to include the line of best fit that go through the data appropriately. This was easy because everything is done for you. They put for you the axes, they've labeled them for you, everything is easy. So just inputting the points was the needed part. So I will just go to the next part. So here let's see. They continue to say the relationship between the S total and 1 over T can be formed by combining the equations. So we have these equations to give us this. Of course, you guys know from your textbook, the S total is equal to the S system minus negative, of course, minus dH over T. Negative dH over T is the S surrounding. So they continue to say, determine the gradient of the line plotted in B including units. We'll go back slowly. To determine the gradient, you will have to find suitable points, at least suitable points through which the line went through from your data, and then you put them. All you need to know is gradient is going to be change in y divided by change in x. Find suitable points from the graph or from the line, and then you can just substitute and be able to find the gradient. This is really easy. The way you do it in math is going to be the same way you do it in chemistry. So let's continue to the next part. They say identify the thermodynamic quantity that can be obtained from this gradient. The value we can get from the gradient is going to be, of course, enthalpy change for the reaction, which is in kilojoules per mole. The next part says determine the temperature at which the reaction ceases to be thermodynamically feasible at a pressure of 100 kilopascals. So it will cease to be feasible if the S total is equal to 0, so at that point. And then the S total is going to equal to 0. So basically, let us go back. Let me see. So we can see if it ceases to be 0, I'm going to take you back the other side. Ceases to be 0, it's going to be when you look at this data here, when the S total is equal to 0. So when 1 over T, at 1 over T, we have that point, and at T is going to be, when the S is equal to 0, we have T is going to be 1 over that value, and then we can be able to find the T is going to be 465, which is simplified to get us 465 if you take away the decimals. So, and again, I want to show you, this is going to be 0 when 1 over T is equal to that. And then, because it's 1 over T, T will be equal to 1 over that value. When you use your calculator, you're going to find 465.116, and then you'll be able to find the other answer. If I take you back to the graph, I think even if I don't take you back to the graph, you have already seen it. This data is got from the graph. We have 1 over T, ds total. If the reaction ceases to be, we have ds total when it's equal to 0. You can see the value is about here. 0, so 1 over T is going to be 0.02 something. If you look at the graph, for me, I got 0.00215, taking you back, 0.00 somewhere, 215, about that. So again, to go back, that is where I got that value. And since 1 over T is that, make T the subject, and then it will be 465 Kelvin. So let us continue to the next. D. The industrial synthesis of ammonia is given by this equation, and they say it's carried out at pressures of about 20,000 kilopascals and temperatures about 700 Kelvin. under 750 Kelvin. These temperatures are higher than the answer in C3. State the relationship between the total entropy, ds total, and equilibrium constant K. This question is very common. ds total is our natural log of K. So that is very common and it's easy to remember. So they say calculate the value of the equilibrium constant K at 750 if the S total at 750 is given to that. So we will fit this into this equation we have got up here. The S total is our natural log of K. We know R is 8.31, and then we can substitute this because this is that, it's given there, and then make natural log of K the subject basically, and then be able to find K as 0.01071. The next part of the question says, again, I want to use highlighter here. Let me use a different color. It says, explain why the S total decreases with an increase in temperature. So, of course, you know this. The S total is the S system plus the S surrounding. And the S surrounding is negative delta H divided by T. So, we know that if it's negative delta H divided by 2, and of course we know the forward reaction was exothermic, it means this whole value is going to be positive. And if it's positive, it means if it's positive yet increasing temperature leads to a decrease of the whole thing, it means actually the increasing temperature will decrease the ds surrounding because the temperature divides the delta H. A delta H divided by a bigger temperature gives you a smaller number. And since H is negative, delta H is negative, it means it gives us a whole positive from within here. This part here is going to be positive, but it's going to be smaller because you're dividing it by temperature. That part becomes positive because it's negative of delta H over T. However, delta H itself is negative because it's an exothermic reaction. In the end, it ends up being positive delta H over T because the whole thing has been taken into consideration. And if this is big, the whole thing is going to be smaller. And now you have a small thing that you're adding to the S system. Since the S system will remain unchanged, it means the S total is going to decrease. So here I say the S system and the H do not change that much when temperature is changed, of course. So the decrease in, of course, the total entropy, there should be a decrease in the S total. And since the S total is negative, the S total is going to be the S system and the S surrounding. Here the S surrounding is negative delta H over T. The forward reaction is, reaction is exothermic. It means there is going to be a decrease in the S surrounding, which leads to an overall decrease in the S total. I'll continue to the next part. The next part says, state how the Haber process is made feasible. Let me get a highlighter here. Is made feasible at 750 Kelvin, even though the total entropy change is negative. Here we have to know they are working at high temperatures for an exothermic reaction. Remember, they are working at high temperatures to increase the rate of reaction. However, it's an exothermic reaction. So this reaction, the increase in temperature decreases the yield because exothermic reactions prefer to have, of course, cooler temperatures. However, if the temperature is lower, it means the yield, the rate of reaction is not going to be that much. So there is going to be kind of a compromise. Using 750 enables the speed or the rate of reaction to be faster. And then the unreacted products, I know it's going to be faster and the reaction is reversible. However, they are sure that the unreacted reactants can be recycled and be used in the next process to be able to make the product. So I said working at high temperatures for an exothermic forward reaction decreases the yield of the forward product. So what they do, the reactants are recycled to increase the yield. And again, the question was asking you how the Haber process is made economically feasible at 750K. 750K increases the rate, however, it decreases the yield. So to compensate for the decreased yield, products are going to be recycled in order to be used in the next step. And the next they say, ammonia from the Haber process reacts with acids. With phosphoric acid, a number of products are formed in solution. One of these is a fertilizer, the ammonium, hydrogen phosphate. They say write the equation for the production of this fertilizer. So it's the ammonium hydrogen phosphate. Of course, if it's made by reacting ammonia and phosphoric acid, It means they are combining to produce one. In this case, a proton is going to be, of course, gained by this one here to make it ammonium. So again, this is going to be, this loses a proton to that to make it ammonium. Now we have a cation, an HPO4 minus, and then they interact. When the two minus, when they do interact, they're going to form something which is going to be like that, which is that this one here, which is going to be diammonium phosphate. So they will come together because two hydrogens, actually two were left. So if it was two here, it will be a one. But since again, I want to make this one better, it's supposed to be HPO4. It means it's a 2 minus because two hydrogens are left. They went to the two ammonias, and then they will combine, forming that product which we have there. And then next, write an ion equation to show that ammonium ions are acidic in aqueous solution. So of course, this one I'll say ammonium is going to be broken down to produce ammonia and H+. This is showing that it's acidic because it's a proton donor. Let's continue to the next part. Lastly, a solution containing both ammonia and ammonium ions acts as a buffer. Explain using a relevant ionic equation the effect of adding a small amount of acid to this buffer. Again, this is what we have seen previously. So when ammonium donates a proton, and breaks down or dissociates, a proton is going to be released and ammonia is going to be generated. So this is the buffer. So in this case, we have a large reservoir of that and a large reservoir of that. So I said, because the mixture contains a large reservoir, this is very important in any answer, a large reservoir of both the ammonium as well as ammonia. When small amounts of H+ are added, the added H+, of course, adding small amounts of H+, let me show you, they will react with that, producing ammonium. So they react with ammonia, producing ammonium, as the equation shows here. And this will use up the added H+, minimizing the change in pH, because there will be no free hydrogen ions of those that have been added will be used away. And then I say the ratio of the NH4+ and NH3 is hardly changed by this, meaning the pH remains almost constant. And again, remember here they're asking you when small amounts of acid, they did not talk about small amounts of alkali, so my only interest is in the acid. When you add small amounts of acid, they will interact with ammonia, reacting to form ammonium, and there will be no significant change on these two, or I would say the ratio of these two will not be changed, and therefore there will be no overall change to pH, or the pH remains almost constant. So there is another alternative you could use. If somebody used this equation, then you can talk about the explanation as you see here. So when you hear, you can say when small amounts of H+ is added, it combines with this, producing water, and then the ammonia reacts with the water to produce OH-. So basically, it's going to be like that. So there will be no significant change in the pH as well. This brings us to the end of this section, which is section C, as well as the whole end to the paper. This is Unit 4, January 2022 for Pearson Edexcel. Thank you for being with us. Please remember to subscribe, and I will see you in our next video. Bye-bye.